Alright everyone, let's start with some graphical approaches to iterative solutions. And to practice this, I am going to show you the using the Aragon equation. I have over here a spreadsheet set up already that describes the Aragon equation here, and you can see I've created a table of variables with already some information plugged in. Just really quickly, if you look through this equation, you have the pressure drop, which I'm defining as the change in pressure with respect to the length of column. This term here, I'm going to set this at 2,000 pascals per meter. Shape factor here, which is the shape of the particle, setting it as 1, so it's consuming spherical particles. I specified a diameter of the particle. In this case, here you can see it's a 0.001 meter particle or 1 millimeter particle. I'm keeping all of these at equivalent units to make the conversions easy. Superficial velocity I set at 0.1 meters per second, which is probably reasonable for a gas. Viscosity, and in case you're wondering what superficial velocity is, that is actually if you assume there's no packing in the material and you're flowing a volume of air through a column, you take that volume of air divided by the cross-sectional area of that column, and that gives you superficial velocity. It's probably not the actual velocity because obviously there's packing, and so it's going to be at every single domain as it's moving around that packing. It's going to be a little bit faster or a little bit slower, depending on, or a little bit faster, I should say. But you get the idea on how that works. The viscosity is set here in Pascal seconds. And usually we refer to viscosity in terms of poise, but here it's just, I'm already doing Pascal seconds just so everything else kind of fits uniform variables or uniform conversion, so I don't have to do anything, and all these will cancel out in the equation. All the units will equal. And density here is 1 kilogram per meter cubed. All of this is probably accurate for a gas stream going through a packed column. But now finally, what I really want to know though is, and what we want to know is, if we have a given pressure drop for a column like we have here, and we know superficial velocity, what is the porosity it's going to achieve? So the simplest way we can actually try to find a solution for our porosity is to actually go ahead and come up with a way to plot this expression and then find a way to reference where that plot behaves as a function of this epsilon. And if we can somehow relate it to some other factor on that plot, we can find a solution. So how can we do that? Well, the simplest way is to think about in terms of functions. If we have a function of x, in this case, let's just say it's x instead of epsilon as we have above. Let's say we have f of x. Now, in an expression, if we have f of x as equal to some massive thing, if we bring all the terms in that expression onto one side, then we know that function, when everything is satisfied, is going to equal 0. And so if we took, for example, here and pulled all the pressure drop and moved it to this side of the expression, this whole right-hand side will equal to 0. So if we just plot the right-hand side as a function of epsilon, our porosity, then the point at which it intercepts the x-axis is the solution to this expression. So we can do that. So all we need to do is come up with a plot. So I'm going to take our porosity epsilon, and I'm going to then create a f of x, or f of epsilon, I guess technically, and plot epsilon versus f of x. So I'm going to first create and separate these two terms out. I'm going to term 1, term 2, just so it's a little bit easier for us to enter in. And so I'm going to say 150 times our superficial velocity, F4, times our superficial velocity, and times our viscosity, right here, F4, divided by our shape factor, F4, that's actually squared. Although it's 1, I don't need to do it. I'm just doing it for completeness. Our diameter of our particle, F4 squared, now times this epsilon term. And so this is going to be times 1 minus epsilon squared divided by epsilon to the third. And that should be it for that term. It's divided by 0 error, of course. So I'll just put this as 1 so we don't have to see that as ugly as it is. And then we can put term 2 here. I'm going to scoot this over so we can read it. And it's going to be equal to now 1.75 times our density F4 times our superficial velocity squared divided by our shape factor divided by our diameter for particle. And let's double check. I forgot to lock these in, so lock those in, lock this one in, and then we finally have this final term here. So that is times 1 minus epsilon divided by epsilon cubed. So we have that term here. And now our function is simply going to be our pressure drop, which gets locked in, minus this term minus this term. So now we can actually start plotting this. I'm going to say 0.2, oops, let's copy this down, 0.3. We can copy these down, and now we'll just copy all these down. Porosity only goes from 0 to 1, so it doesn't really make sense to go beyond that. But we can take all this here, these terms, go to Insert, go to a line plot in this case, and look for the point at which it intercepts the x-axis. And so we can do that by zooming in here. We're really big. This equation's pretty crazy behaving. So I'm going to zoom in, let's say 0.5 on the x-axis. That's still pretty hard to see. And our y-axis isn't changing. So let's zoom our y-axis in as well. Let's make it minus 100, 1,000 to 1,000. Oh, there you go. Now you're starting to see where the line is intercepting here. And it's going between 0.85 and 0.9. We can zoom in to that range just by changing our axes. Oops. We can zoom in to that range. Axis options. We can zoom in to go to 0.85 to 0.95. And you can get a pretty good estimate of what the intercept is. It's somewhere between 0.87 and 0.88. Or 0.875 is probably a good estimate for this porosity, 0.875. So if we went up here and just said 0.875, you'll see we're actually not too far off compared to the magnitude of numbers that we have here. We can get even better values if we put 0.85 and then plot this 0.86. Then we can go down even further and get a more finely tuned resolution of what the answer is. But you'll see we are somewhere between 0.86 and 0.87 for the porosity of our sample. And we can zoom in further and further and further to get a solution. And you'll notice now, using this function, the graphical approach, it's not just where you can find it through the plot, but you can find the solution by actually also looking at the point where your signs change on this plot. So in this case, I can go 0.861, and I can have that 0.862, and we can start to zoom in even further with this by looking at the point where it inverts from negative to positive. So our answer is somewhere between 0.868 and 0.869. And that is, in a nutshell, how you do an iterative solution using the graphical method. It is literally just taking a function, converting it to f of x is equal to 0, for example, and plotting that term and finding out where it finds the intersection with the x-axis. The advantage of this, you can see here, We can do this by looking at where it inverts, and that's fine. But you can also do this for solutions where you have multiple roots. If you have a cube root equation or otherwise, and there might be multiple answers to this, you could actually use this as a way of finding all of those answers all at once. And you'll notice this is exactly what you have to do for your homework. So I encourage you to think about this and see if this makes sense. And so we'll go to the next video for another approach to iterative solutions. So thanks.